All right, so we are with Assistant Professor Baptiste Journeau with the University of Washington, who's going to talk to us about some of the goals of the Artemis Moon mission in terms of actually putting people on the ground on the moon and what they're looking for. So, Professor, I want to start by asking you what you know about NASA and the European Space Agency's plans in terms of conducting science when they get back to the moon for the first time in 50 years.
Yeah, so thank you very much. The general idea of this new era of missions is really like to push forward where we left the science, like in the early 70s, really, when the last samples were brought back on Earth. So one thing to understand is that most of the samples that were brought back at that era were mostly from areas on the moon that were easily accessible per se, even though like going to the moon was really hard in the 70s and it's still really hard. But landing on the equator, which is on close to the equator, which is what the Apollo mission did, on very flat surfaces, like on the mares, like the very flat seas. So it's not a real seas; it's like old lava lakes that solidified, but are very flat. Is much easier to do than what NASA is planning on doing for the Artemis missions. So the goal of the Artemis mission is actually to land on the southern pole of the moon, where we expect that there is a lot of water. Ice in the form of ice mostly. And the reason why there is water there and not in other places is because there is craters there that are constantly in the shadow, that never see the sunlight and probably haven't seen sunlight in like billions of years. And so scientifically, it's very interesting because these ice are actually probably coming from comets, some very old object in the solar system. So they could teach a lot to us in terms of the origin of planets and the origins of life as well on Earth, among other things. But also like there is all the areas in these at the poles are actually much harder to arrive to because they're in very mountainous areas. So NASA needs to be able to do very precise landing there. So it's going to be quite hard. And so that's one of the many things that's going to make these missions like absolutely fascinating.
It's funny too when you said it was much easier, and you acknowledged that it was hard anyway to get to the moon. I'm willing to bet Neil Armstrong would have disagreed with you, considering he had to switch to manual and fly over a bunch of boulders to make a safe landing there. So, but no, I get what you're saying. And, you've just said a lot that I've actually been thinking about, and I want to unpack. So let's take this one piece at a time. So you had mentioned that the water ice that's there along the southern pole of the lunar surface probably comes from comets or somewhere else. So would that also be the reason that we have the craters there? We're looking at the impact, and then the ice itself then gets planted on the surface?
Yes, exactly. Like either through passage of comets over the last few billion years, who just like drop like ice grains on the surface. And because there is never lights that arrive there, because it's always in the shadows, because it's at the poles, yeah, it can be conserved for very, very long times indeed.
But we're saying we don't think it's necessarily possible that as the moon was being formed, there might also have been some water deposits that were left there and frozen. I mean, is that basically a statistical impossibility?
Yeah, no, I don't think so. Like the last, like the moon formed from a giant impact, or at least that's the current theory of a giant impact with the proto-Earth and another protoplanet that was roughly the size of Mars. And so the moon formed from this, hot magma that, solidified And the latest major geological event on the moon were the giant impact that formed the mares that we see. And these would not have, deposited a lot of water, I think. So, so most of the water we expected coming from comets, as far as I know.
So I want to back you up also to what you talked about in terms of the samples that were brought back in the late 60s and early 70s. What did we learn from those? And I know we've squeezed a lot of learning out of them in 50 years, but what have we learned, at least from those, about the basics of lunar geology?
Oh, so quite a lot of stuff. Actually, it will be hard to summarize everything in an interview. But the main thing that we have learned, I would say, were like probably twofold. Like the main one that I can identify is just understanding how the moon formed, because the moon is a very large satellite if you compare it to all the other objects in the solar system. Most of the other planets of the solar system have moons that are much smaller to their actual size, like as a ratio. So that was already like quite a curiosity, like scientifically, to try to explain why the moon was so big compared to all the other moons in the solar system that we see, and compared to Earth, and how did it form. So the rocks that were brought back by the Apollo missions, but also a little bit by the Russian missions as well, allowed us to actually identify like the full history of the moon formation. So with the giant impact and the formation of the mountains and the mares, and also like explain, for example, why the lunar core is really small, for example, because most of the iron during the impact actually went into Earth. That's one of the things, and it's something that we could verify with the seismometers that were also landed during the Apollo era. So that's the first thing. And the second thing, I think, is a very important contribution from the samples that were brought back, is how to date the entire solar system. Because currently, the only way we have to measure the age of planets, or of surfaces of planets in the solar system, is by literally counting all the craters at the surface. Because the longer time passes, the more craters there will be. And so, but at some point you need to calibrate the scale. And because on Earth we have an atmosphere, we have tectonics, we have erosion, we cannot use the amount of crater on Earth to calculate an age. It's not possible. There's too much that has happened since a crater occurs. And so on the moon, we were able to bring back these samples, date them very precisely, and then actually count the craters in that area, and make very nice calibration curves for the age versus the number of craters. And this is what is used now on Mars, on the icy moons on Europa, for example, on Enceladus, etc. So getting more data on this will definitely help us to fine-tune our ability to date the solar system in general.
Now, Professor, that begs the question, how old is the moon?
Okay, so the moon is slightly so very slightly longer than Earth. Yeah,
4.5. Okay.
Yeah, so it's very slightly younger than very so slightly younger than the Earth.
So the other thing, in the limited reading I've done on the Artemis plans, is that I've discovered that there might be different geological formations, different types of rock, things that weren't necessarily found in the equatorial landing sites. And as I understand it, the probe that goes around was able to sort of detect that. I know we've had a device in orbit of the moon for quite some time with some sensors on it that's able to detect that. What do we think we're going to find, other than the water ice, of course, that's different at the southern pole?
So geologically, the areas that were sampled by the Apollo missions were mostly in the flat areas of the like close to the equator, and these are very particular geologically. They are much more recent. So these are the ones that are like around 3.8 billion years, because that's the later impacts that happens. That's the late heavy bombardment. That's the name we give to this event. And so because of that, they have a very specific chemical composition that is probably pretty close to lava that you can find, for example, on in Hawaii. But the rest of the moon, the white part of the moon that we can see with the naked eye, are the one that we expect, for example, on the poles. And these are much older, and probably comes from the very primitive crust and first formation of the moon. So we expect to find like a much like to find like a lot of very, very different rocks there that would actually tell us a lot more about the very early stages of the formation of the moon.
And I would guess that we would extrapolate from that the early stages of the formation of the Earth.
To some extent, yes. Yes, to some extent, yes, and other planets in general. Because yeah, like the type of rock that you will form very early, if they have been preserved for so long, will tell us how a planet forms like at the beginning. So that will definitely be something that will be interesting for Earth as well, because most of the rocks from the early Earth have been totally erased, most of them. Like, I mean, there is no rocks left from the first few million years of the Earth. Everything has been eroded or recycled through plate tectonics.
Well, then we still have a lot to learn about our own home, which I find incredibly fascinating. Now, I might be straying a little from your area of expertise, but there's also value of not only landing, but maybe setting up a permanent settlement near where that ice is, isn't there?
Yes, there is, yeah. And the importance of finding water is actually I think understated for a permanent stay on the surface of the moon, because water can be used for oxygen, so for breathing. It can be used for for drinking, of course, for growing food. So lunar soil cannot be used just mixed with water and make growing soil. It doesn't work that way. You have to add organic matter to it, of course, and also other elements. But but that could be used eventually. Why not, to grow food on the moon? And also it could be used as fuel. If you use, for example, cryogenic engines with hydrogen and oxygen for the return from the moon, you could actually mine the fuel directly there. And that would help a lot to make the base like independent from the Earth quite rapidly. So that's very, very important.
Well, and you had mentioned it, using it for maybe for the return trip, which of course, having to pack less fuel means you can take the weight for more equipment up there,
Exactly.
which is equally as important. But in my mind, I'm thinking it's not just for the trip back. It could also be used for a trip forward, couldn't it?
Yes, exactly. Exactly. It could also be used to go further than the moon. Exactly. And I guess that's that's really like the next step, or like the step after the next step, because the next step is the Lunar Gateway, which is part of the Artemis program, where we're going to have International Space Station. Then instead of being like the current one around Earth orbit, low Earth orbit, is going to be around the Lagrange point. So it's an equilibrium point between the Earth and the moon. And that's going to serve as an intermediate between Earth and the landings. So the step after that, logically, would be to have some kind of a semi or a quasi-permanent base at the surface. And that would help to prepare all the technologies for the next leap, which we expect to be Mars, but who knows when.
I will share a personal opinion with you. I don't think we should have stopped going to the moon in the 70s. And if we had continued along this path then, we would have been to Mars probably before the year 2000. That's just my personal belief. I could be way off the mark, but I think we could have advanced a lot farther, a lot faster. But again, I could be wrong.
Yeah, well, it's an interesting thought experiment. I think there is a TV show that does that pretty well right now. I'm sure you know it.
You're probably thinking of For All Mankind on Apple TV.
Exactly.
Absolutely. But even before I started watching that a couple of years ago, I kind of felt like, we should have been back. Now, you're pretty well versed on this. Do you have plans at some point to go do some field work up there?
I wish. I wish. I think I'm unfortunately a little too old. And also, like, if I had to do some field work, I would have to either become a US citizen or get selected by the European Space Agency. So maybe, but for me, it's not planned.
Well, I will tell you, not only am I hoping to be the first reporter to, be live from the moon as a reporter, but really what I'm in more seriousness, what I'm counting on is in my lifetime, we get to a point where there might be some lunar tourism. Because if I die without having been to the moon, I am going to consider and I've had a great life so far, wonderful family and all of that. But if I die without getting to the moon, my life will definitely be incomplete. So hopefully at some point we get there and we're able to do the science.
Yeah, I hope we get there, but like there is like so many technical challenges that, I think that like the fact that the Artemis program is an international effort rather than just a pure US effort is actually a step towards the good direction, because a lot of the technical challenges are like things that one nation cannot face by itself, I think. So
Oh, I totally agree with you there. In fact, I think the ESA is an extremely valuable partner, as are the Canadians and the Japanese. And frankly, it's a shame our relations with the Russians have soured, and that has reached our space program, because they could be an amazing partner too. So, we have enough out there to get us going, and I think we're making a great step forward. Professor, did I miss anything you think we ought to be thinking about?
I don't think so. I mean, like, of course, many things, but I don't think we have enough time. But yeah.
And honestly, I don't have the intelligence to ask that many more questions. You're the expert there, and hopefully, fingers crossed, someday. I'm sure you know who Harrison Schmitt was from Apollo 17, the only lunar field geologist. I'm going to make you jealous here. I got to interview him several years ago. What a huge thrill. I was equally as thrilled talking to him as I was getting to talk to Buzz Aldrin. And Dr. Schmidt's partner, Gene Cernan. Got to talk to both of them, which was great. But just to be able to do the science on the ground, to me, I think, is the most important part.
Dr. Schmitt experience is something quite unique. I've met him a few times at conferences and exchanged with him a couple of times directly. But like we have actually, there is actually one professional geologist already in the NASA astronaut corps, which is like Jennifer Watkins, I think, who is currently on the ISS. And so she has a background in Mars geology. So I think she has a very good chance to be the next geologist on the moon, I think. I hope so. That would be nice.
I hope so too, because like I say, that science on the ground is incredibly important. All right, Professor Baptiste Journeau with the University of Washington. Thanks, Professor. Appreciate that.
You're welcome. Thank you very much.